You push and hold the button, the blue lights come on. That means Zoom can hear you. So with this, when the lights are on like this, Zoom can hear you. You push this button here and hold it to make it quiet. So after you do your introduction, sit down and make sure you turn it back on. For you, based on. That's on.
Shall I start in? Shall I start now?
No. All right, so you can see that it's doing the closed caption stuff.
Yeah.
So, we'd rather it showed closed captions up there, but okay. I already clicked on this. So that one is for the room. We're trying to make it all one microphone, but it's not getting us. Zoom and everything. You can flip it right here if you want to. Just clip it on there. You can put on your pocket.
So I'm not supposed to use that. I am supposed to use.
For you will use, when you do your introduction, you'll do both of these like this. Okay. Here's your. It doesn't just click on the slides.
Okay. Hi, quiet please. Welcome to the second colloquium of the year in physics department. I'm Economou, I'm a professor in physics and ECE. I'm very happy and honored to introduce to you our speaker here. She's Professor Sophia Economou from Virginia Technology, and she's going to talk to us. She's going to talk to us about control and distribution of entanglement in quantum networks. Let me just introduce to you her background a little bit. She has a very distinguished career. She got her PhD in 2006 from UC San Diego. After that, she worked at the US Navy Research Laboratory from 2006 to 2015. And since 2015, she has been a faculty member at Virginia Technology in physics department. Since last year, she has held the T. Marshall Horn Chair in Physics. And since 2 years ago, 2021, she has been the director of Virginia Tech Center for Quantum Information Science and Engineering. And she has done a lot of very interesting, exciting research work, which we will hear here, including quantum networks, quantum control, quantum computing, and quantum algorithms, right? And if you look at her research books, right, she's extremely productive. And I was struggling to her that she wrote so many exciting, interesting papers, right? Much faster than I can read, really. Okay, thank you. We'll hear about that.
Thanks a lot for the nice day. I'm very happy to be here. My first time in Toronto. Great place, and also I'm very lucky I'm visiting it now that we have a great weather. All right, so I'll start by some general introductory things that some of you may find very familiar. Hopefully, it'll bring some debate, and then I'll get into more things on the line. So I'm sure we've heard a lot of talks about quantum technology, quantum computing, your environment at the Brown University, very active in this field. But just to make this at the open level, I want to say some things that are basic. So we're talking about quantum systems, qubits in particular. Everything I talk about is discrete variables, so two-level systems. And of course, the things that make quantum mechanics, quantum technologies different from classical are things like superposition, very notably quantum entanglement. Quantum measurement is different. It's probabilistic and recursive, and it can change the quantum state. And then for networks and cryptography, also the non-cloning theorem, meaning that we can also be unknown quantum states. And that one will play a big role in the talk. First of all, play a big role in technologies. So I'll talk about pure states law in this talk. That one qubits can be thought of in this way. You can say in family, you cannot write it down and depends the product of the different states or the two constituent systems. And then a prime example of examples. And I will be using this schematic, which for now will be so the circle denotes the line denotes entanglement moderation of the qubits. So this whole thing denotes you can think of this as a bell state. And it'll become more rigorous, but for the first part of the talk, I'll just use this. Focusing down to quantum networks, my group works on various quantum information computing, but for this talk, I'll be focusing on networks. And there's various reasons we want both of these things. One is to do quantum cryptography, which you can achieve various cryptographic protocols securely, unlike you can implement certain protocols of this synchronization or sending based on protocols. And then an interesting obligation can access cloud quantum computers and securely. And the cloud obligation is arguably something you cannot do fast. I also wanted to highlight a few papers that have formed. I saw another collaborative sprint that was here from quantum physics that has basic information about quantum. Okay, so let's think about the simple thing you might want to do. A very simple thing you might want to do is you might want to share a bell state between parties that are far away. So one of these parties can prepare a bell state, you can use photon or not photon, and keep one of the qubits and send the other down an optical fiber to the party. The problem is that these optical fibers are lossy. So after a certain length, your photon is guaranteed to be short. So you're going to lose your bond. And you cannot just mimic with the classic methods and amplify it because quantum information cannot be copied and it's method. So one thing you could think about is chopping the distance a little bit. So you can bring another party here in the middle, who can prepare the bell state instead, and then send each photon to the part. Right. So what we achieve here is chopping the distance. Now, but that result is not sufficient. Prepare two bell states actually, and send half of each to the other. Have these prepare two bell states, and send them one to the left, one to the right, there. This middle party makes measurement. And a very key feature here is that this measurement is an entanglement base. So when this measurement happens, these two qubits here end up entangled. Doesn't work yet. The fact that they're both will be destroyed. We'll get to that in a moment. And upon this measurement, this magic things happens here, where these two are entangled, there's entanglement transferred to the output. So you're using entanglement as a resource to prepare an entanglement state. You can do this never need to interact. Right. So this is kind of the basic idea of how you extend entanglement in quantum. And this is called entanglement swapping. And it's also parallel to entanglement because upon measuring things, you know that these are also entanglement.
I swap you out. This one is, that one's gone quiet. So.
Oh. All right. However, we're not done yet. And there's still something that prevents us from establishing the entanglement we're looking for. And these parties are sad because the photons can still get lost, right? So even if you chop the distance, there's still some probability that the photon will get lost. And moreover, this Bell state measurement is probabilistic for photons. So 50% of the time it's not going to work, and you have to discard that try and send a new pair of photons. So if you were to just try to scale this up this way, you'd have a problem because your rates would just blow up, would just go to zero, right? Because all of these would have to succeed at the same time, which is increasingly unlikely. So instead, what we can do is we can use quantum memories, which are matter qubits that we're assuming have a very long coherence time. I'll get to that in a moment. And then you can just repeat until success. But the key point here is that you can store the successful events locally into the quantum memories, right? And that way you can hope to beat these rate limitation. So this is the schematic of how it would work. Now I'm using blue color for the memory qubits and green for the photons. So each memory qubit emits a photon in a way that the two form a Bell state. And then these photons are sent into some intermediate node for the Bell state measurement, right? And this Bell state measurement can fail. It does fail 50% of the time. But when it succeeds, then we have entangled the blue photons, right? Because of this entanglement swapping. And now we're, I'm sorry, the blue qubits, the matter qubits. Now we're assuming that these matter qubits are very, very long-lived, which is a very big assumption. But let's just go with that for now. And then when all this has happened and all of them have succeeded, you end up with Bell states of memory qubits. And the very last thing you want to do is get rid of your memory qubits in the middle of this line, because at the end of the day, you want one Bell pair between the remote parties. So now I need to do one more projective Bell measurement per node to entanglement swap here from here to here and from here to here, etc. So if I do that, then I can sequentially, these operations I'm assuming are deterministic. That's another big assumption. But let's assume that's the case. Then I end up with this Bell pair that's between the two remote parties, right? So a key element here is this quantum memory, this qubit that can generate a photon into a state that's a Bell pair between the two. And to realize that, we can do it various ways. Here, I'm just drawing a generic 3-level system, right? If you have taken an AMO class, this should be familiar. But it's the only difference from a qubit is that now I have a 3rd level to which at least one of the qubit levels can couple, right? And here we're making the simple assumption that only one of these qubit levels couples to the excited state, right? And you can achieve this through selection rules or other way, but this is not a sweeping assumption by any means. So what you can do is you can prepare superposition of up and down the 2 qubit levels, excite the system to the excited state. Only the spin up will, or the qubit up state will be transferred to E. And then you can get a superposition between down and E. And then if you let the system relax, a photon will be emitted and you're going to get this Bell state. So here I'm using the occupation degree of freedom of the photon as my qubit, right? There can be 0 or 1 photon in this particular mode. And we're making some assumptions that there's just one photonic mode here. Right, so then I can achieve spin photon entanglement this way. So there's many ways you can do this. You can do this with atomic systems, trapped ions, quantum dots, etc. The system I'll focus on today is a defect center in diamond. So a lot of the work I'll talk about, at least the first half, will be focused on the system. So I'll walk you through the key features here.
And then some of the later work I'll show you is a little bit more general. The reason I'm focusing on this is that this has been pursued quite heavily, especially by a group in Europe, in Delft, Netherlands. And I think in terms of solid state quantum networks, at least, it's state of the art. All right, so what is an epicenter in diamond? So diamond, of course, consists of carbon atoms, and it can have defects, meaning that carbon atoms can be missing and some other atom might be substituting them. A very common defect in diamond is nitrogen. And another common thing that can happen is that next to the nitrogen, another carbon atom is missing. So this combination, these two local imperfections in the lattice are known as an envy center. Okay, so that's all we need to know about what an envy center is. And what is important here is that there's a lower level manifold here. So this is a multi-electron state. You don't need to worry about that. The only thing to keep in mind is that this is a spin 1, total spin 1 ground state, right? Which with addition of angular momenta, you can see how you get it. But for this talk, you don't have to worry about that. And since you have 3 levels down here in the ground state, you can select 2 and call those 2 levels your qubits. And you can do microwave drive between the 2 levels, so you can implement qubit operations. One important thing is that there's a strong transition, optical transition between state 0 and the excited state. And you can use that to implement the 3-level system I showed you before, right? And you have selection rule here that you can only focus to this transition. So you can use your 0 state, 0 here meaning spin projection 0, and one of the 1 states as your qubits. And let's just ignore the other one. Okay, so out of this, all you need to focus on is this green transition. Right, so then schematically, oh yeah, and I should also say that in addition to the microwave, you can of course also optically control it, which is a requirement. So schematically, this is how this would work. And this is just piece of our quantum network, right? I'm just taking the 1 optically active qubit over here. It emits a photon. This is an entangled state. This is an entangled state. And the photons come together in some beam splitter followed by a measurement. And this is an experiment that now has been done multiple times. An impressive implementation was several years ago now from the Delft group I mentioned before, where they showed entanglement and Bell inequality violations for over 1 kilometer away. So these are 2 different labs that are separated by more than 1 kilometer. And there's this lab C where the photons are sent and where entanglement swapping happens, right? So this is a part of the whole, all the pieces you need, right? It's not everything though, because we still haven't talked about locally the quantum memories, right? We only have 1 qubit right here. But if we go back to this picture, right, remember that we need at least 2 qubits per node. So 1 envy center won't do. We need 1 more thing. And this 1 more qubit can be found also in this diamond lattice. And it can be selected as a carbon nuclear spin. So carbon, the vast majority of carbon has a total spin of 0. So that means no qubit. But there is a 1% probability that the carbon will be carbon 13, which is a spin and a half system. So there's a nuclear spin that's non-zero there. And these can be, it's a small enough concentration that you can harness its quantum properties without it being totally a bath that destroys your qubits, as you could have in a platform where it's all spinful nuclei. I can talk more about that later if you're interested. So you can actually hope to get good memory qubits out of this lattice. So let's see first, kind of in a cartoon way, how this repeater scheme would work, or the network. So now, instead of just 1 qubit. I have a bunch of qubits per diamond or per sample. And now my MV, which is this purple arrow, can emit a photon that's entangled with it. And if this Bell state measurement succeeds between the photons, then I establish this entanglement link between the MVs. Now, I want to be able to use this MV center to establish another entanglement link with a different direction, right? I don't just have 2 nodes in my network, I have a bunch. So what you can do is you can swap the state and store the quantum state onto a nuclear spin. We'll worry about how you do that in a moment. And that way you have now entangled these 2 nuclear spins, which can be located very far away from each other, right? Kilometers away in principle, which also never interacted with the optical field. They're not optically active. But you've done that through this interaction that enables this swap operation. And now your purple spins here, the MV center is free, and it can be used for another entanglement attempt with some other node in the network. So this way you can now connect these 2, and you just concatenate this product. Also, if there's any questions during the talk, I'm happy to take them. All right, so there's been also an experiment involving nuclear spins in the system by the same group. This was much more recent, where they used a nuclear spin, a memory qubit, and they showed genuine 3-qubit entanglement, a GHZ state, right? These are very difficult experiments, and you can see that, the other one was from 2015, this is 2021, to go from 2 to 3 qubits. So it's an experimentally difficult thing to do. All right, so let's go and now think, how do you actually implement these gates that you need in order to transfer your quantum states to your memory qubits? That's going to be part of the first part of the talk. So physically what happens is you have some Hamiltonian that describes coupling between your central spin, your optically active MV center, and these other nuclear spins that are sitting in the lattice. And this is a magnetic dipole Hamiltonian, right? So it has some directionality, and M1, M2 here are magnetic dipoles, or you can think of them as spin operators. Now you can make some approximations using the fact that nuclear spins have a small Zeeman splitting compared to an electron. That means that it's unlikely that the electron will flip as a result of the interaction with the nuclear spins. So you can think of the electron as being fixed along some quantization axis Z. And here Z and X denote Pauli operators. And the nuclear spin, however, can flip with interaction with the electron. So the Hamiltonian has this form where this is the Larmor frequency, and A parallel A perpendicular are the 2 components of the hyperfine interaction. And an important point is that because the hyperfine interaction cares about the orientation and the distance of the 2 dipoles, you're going to have essentially a knob, depending on where the nuclear spin is sitting, that controls how much and what form of interaction that has with your MV center. So not all nuclear spins are coupled the same way with your MV spin. All right, so in principle, I have the ingredients I need because I have a spin-spin interaction, and now I can run this Hamiltonian in some way, and I can implement a unitary operation, which is what I want. So let's look at a little bit more closely how this Hamiltonian looks like. The projector here, the purple, hopefully this is a colorblind friendly color coding, but this first projector here is an electron spin projector, and the Hamiltonian here lives on the nuclear spin. And for now, I'm just assuming 1 nuclear spin for simplicity. So what this Hamiltonian tells us is that if the electron is in state 0, that particular nuclear spin sees H0 Hamiltonian. If the electron is spin 1, it sees H1. Right. So right off the bat, we have a conditional form of the Hamiltonian, which is, of course, what we want to do conditional entangling operations. And this form of the Hamiltonian is inherited by the evolution operator if I exponentiate this Hamiltonian. Right. So you can think of this as being a block diagonal Hamiltonian for the electron. This is a block diagonal evolution operator for the nuclear spin. All right, so this is a good building block. However, I have to deal with the fact that I have a whole bunch of nuclear spins, each with its own interaction. And these interactions are always on. So unlike cases where I can have switchable couplers, these are always there, and I have to somehow deal with it, right? Even though I want to do one gate between a two select qubits, these other qubits are there, interact with my MV center. So what do? Well, we do what we've learned from NMR from decades ago. We can do dynamical decoupling, which is a way to pulse this MV spin, or you can think of it as a central spin, with microwave pulses, pi pulses, such that I decouple the interaction. So I can send the pulse sequence, and this is a particular sequence, 2 pi pulses that I can repeat. It's called the CPMG sequence because of the initials of the people who came up with it. But of course, I don't want to decouple all the nuclei. The whole point of doing this was to create a 2-qubit gate between MV and one of the nuclear spins. So what I want is I want some sequence that generically decouples all these qubits, but preserves the interaction with one, right? And I'll use the fact that these have a different coupling as my knob to pick which one. All right, so I have 2 things I can change. If I fix my sequence to have this form, and pi here denotes a pi pulse, so an operation that flips between 0 and 1. I have 2 things I can change. I can change how long this sequence takes, this time t, and how many times I run it, right? In this simple sequence, that's all I can change. But this turns out to actually be enough because I can solve the problem with one nuclear spin. And I can see that when the time has this particular form, I can hit a resonance in the sense that that particular nuclear spin that has these parameters over here is not going to be affected by the sequence. So I'm actually preserving that interaction and I'm killing the rest, or at least in a perfect world, I'm killing the rest. And the same group in Delft has done a lot of experiments on this. This was the earliest one. And basically here, they changed this time of the sequence, this t, and they saw these resonances, these dips. And these correspond, don't worry too much about what the y-axis is. These dips correspond to hitting different nuclear spins, right? So, and if you have a narrow resonance here, you're likely that you're just hitting one. All right, so going back to our evolution operator, you can, we already said you can think of it this way, right? If the electron is up or 0, you do a rotation about one direction. If you're down or 1, you do a rotation on the nuclear spin about another direction. All right, so in a perfect world, we're done, right? Because we have a knob to catch, to control one particular qubit out of our memory register, and we're killing the interactions with the rest. But of course, in reality, that's not the whole story, because dynamical decoupling does not decouple perfectly, and some of these parameters could lay close to each other, or some of these resonances could be a higher order frequency of one could correspond to a lower resonance of the other, right? So you need to do something to make sure that this dynamical decoupling sequence you designed is really doing what it intends to be doing. So one brute force way to do it is select your good memory qubit, come up with your decoupling sequence, and then run some simulations to see what does the sequence do to the other nuclear spins, right? And then you can change your parameters and hope that you eliminate the interactions as you intended. But we can do better than that, and I'll show you work from my student Eva Taku on how you can include all the nuclei in the description. So let's go back to the interaction and notice that if I tensor the different evolution operators, I get something like this, right? So if I look at the problem before I solve specifics, I'm going to have the evolution that has the same form as the original one of the 2 qubits. So I have a projector on the MV spin, tensor with rotations on the nuclear spins, and same thing for the state 1. So it's a very specific form, and it can help us analyze the system analytically in a way that we can avoid a lot of kind of time-consuming simulations. So the key thing we use here is something that characterizes the entangling power of an evolution. So you can use something called one tangle, which is shown here. And it's basically the idea is that you isolate one qubit out of your system, and you ask how entangled is that qubit with the rest of the system. This concept was originally proposed for quantum states, but we're generalizing it to quantum operations by averaging over product states. So now I can have some metric to characterize the one tangles of the different pieces of the system, and I can characterize the different nuclear spins or even the MV spin. What is nice for this particular problem is that if I solve the two-body problem, so the central spin, the MV, and one of the nuclear spins, it turns out that the one tangling power of a given operation can be obtained as a function of that of the individual gates of the individual two qubit problem. So it's a many body problem that I can solve by solving the individual two body problems. And you can get quite non-trivial expressions here. I'll tell you in a moment what these G's are, but these are closed expressions that describe the system. And this is for a nuclear spin. You see it's a function of this G1. And for the electron spin, I have a bunch of G's which depend on the different nuclear spins. Now, what these G's are, they're quantities known also as Macklin invariants, which tell me what class does a two qubit gate belong in. So I can take any two qubit unitary, any unitary in a four-dimensional space or two qubits, and I can break it up into purely two qubit piece, this middle A here, and single qubit gates on the individual qubits. This is sometimes called the CAC decomposition, just because people chose this way. So this is a very handy thing, because you can have different evolution operators that look really different because they're equivalent up to single qubit gates. So if all I care about is, do I have a locally equivalent gate to a C0 gate, a maximally entangling gate, then this is a very handy thing to tell me that, right? So you can make classes of gates, C0 and CZ, if that's something familiar, belong in the same class, because I can go from one to the other with single qubit gates. A swap gate is a different class. And there are other entangling classes as well. All right, so then I can define something called Macklin invariants, which are two numbers that specify these classes. So then these are functions of this alpha, beta, gamma here. And a C0 gate has these particular assignment of Macklin invariants. So C0 is a maximally entangling gate. That's often the workhorse of a quantum computing platform. And the point here is that the multi-qubit one tangles depend on pairwise two qubit Macklin invariants. So now if I've solved this smaller problem, the two qubits, I can say something about how entangled the whole thing is getting. And now I can use that as my knob to design gates. I can go to the physical system, take inputs from experiment, these different hyperfine parameters, and ask, okay, I want to maximize the one tangle of this one nuclear spin with the MV, and I want to kill the others. Now I have a systematic way of doing it, and I can optimize my sequence accordingly. Okay, so here I have different hyperfine parameters just to show you. This map, I would say, looks non-obvious, right? But if I pick one sequence, then I can see, okay, if my hyperfine parameters sit somewhere here, what happens? And I can tune my pulse sequence accordingly. Another thing I can do that people have not done before is to create entangling gates between a bunch of nuclear spins at the same time. So instead of doing sequential gates to create a quantum circuit, I can just create a multi-qubit gate at once. And I can, again, use this as a guide. So what my student Eva did, who's the first author in this work, is she went and she looked into the work from the Delft group, where they have actually characterized now more than 27 nuclear spins around an MV center. So they've done very careful measurements. I'm not going to go over how they did that, but they know the hyperfine parameters of a very large number of nuclear spins. And then you can take these numbers and ask, considering these numbers, what are good gates I can create based on this formalism? So this is what she did. She examined 135 different sequences and then asked how many nuclear spins are involved in each gate, how long does this gate time take, and what's the error, right? So this is a very economical way of coming up with sequences that are good, and it can also answer questions of the following type. Let's say I have some sample that has an MV inside that has coupled to this many nuclear spins. Is this a good system? Can I ever hope to use this as a quantum memory or not? Right, you can also set some something like an error correction threshold, and then you can answer a question, you know, can this system ever be able to do quantum error correction for this particular code? And also we're interested in exploring, you know, how generic, because, you know, experimental groups, especially in condensed matter, they find one sample that's really good, and then they build, you know, experiments on that, right? But if you really want a technology, this better be a generic feature, right? Not only one good sample, right? Generically, you should have something that works well. So you can ask, in a generic system that doesn't necessarily have these 10 optimized or selected very well qubits, how well can I really do this? So ultimately, what I'm kind of getting at is we want to answer the question, are these systems really viable for quantum networks? And I think this is an open question. And this is a tool that we're hoping will be useful in determining them. So how am I doing on time? 10? Great. Okay, so I think that's more than enough to talk to you about the second part of my talk, which kind of, I'm leaving you with that question, right, which I haven't answered for you. But you can easily convince yourself it's challenging, right? There's a lot of things in these memory-based networks that have to come together. The fidelities are not yet as good. Timescales are still long. And, you know, this is the statement that I just, the thing that I just talked about. We have now a tool to analyze this, but the gates are probably still not great. Another thing that's more fundamentally challenging in this implementation of networks is that I need to send information about the success of the Bell state measurement of the photons back to the nodes where the photons originated from. So this is classical communication that I need in order to make this work. And this it doesn't matter if you're using MV centers, quantum dots, or something else, right? So long as you have this paradigm. And then, of course, your quantum memories need to be long-lived. So considering this, you can ask, are there better ways to implement quantum networks, right? And there is this class of quantum networks and quantum repeaters that are called all-photonic. And the idea is that, can I get rid of matter qubits at least as much as I can? In my opinion, we can't get rid of them altogether, but can I at least soften the requirements on how coherent they need to be? So there's there's a bunch of different approaches to this. So one approach is to create logically encoded photonic states and keep sending them in a one-way sort of fashion. The other idea is to create entangled photonic states, and I'll focus more on this. So this is a paper by Hoi Kwong and collaborators from about 8 years ago that I found very inspirational when I read it. And I'll walk you through, I think, don't worry about this, what all these things mean. I'll walk you through how it works. But I just want to point out here that you start with photonic entangled states instead of memory qubits. Somehow you create these photonic entangled states. Every circle here is a photon. And then you send the photons away to other nodes. So one difference here is that you don't have any memory qubits staying behind where you have to relay classical information. So to explain a little bit more how this works, let me just introduce what these things are. These are objects called graph states. because they can be described pictorially with a graph. This is a rigorous way of describing them. Every circle is a qubit. Every line denotes a gate. And you can think of a constructive creation of this by putting every qubit in state 0 + 1 and doing a CZ gate anytime you see a line between them, right? So this is a rule. And that way, if you're given a graph, you can write down the quantum state by following this rule. Now, these have nice properties. One nice property is if I make a measurement in the z-axis, I just remove the qubit. And up to single qubit gates, I leave the rest of the graph intact. Another property is that if I measure two sequential qubits in the x basis, I also get rid of the qubits, but I create a connection. So this is crucial because in quantum networks, we essentially want to extend entanglement, right? So this is going to be our friend. Okay, so let me show you a cartoon of how this works. At every node, we create somehow, I'll get to that in a moment, a photonic state like this. And then we send half of it to the left and half of it to the right in a quantum network. So you can think of the blue nodes as where this state was generated, and the green nodes as where the photons are measured. One key feature here is that you have many arms sticking out. That gives you redundancy into doing the Bell state measurement. So if one of the Bell state measurements fails, which probabilistically some will, then I can use the properties of graphs and I can get rid of their neighbors so that I can basically detach these failed qubits, so to speak, from my graph, which is shown here. The ones that succeed, now I've succeed, meaning I established an entanglement link over here. Then I can use the X measurement that I talked about to create the entanglement link. So some of them I'm getting rid of by Z measuring. Some of them I'm also getting rid of, but in a way that I create an entanglement link across. And an advantage here is I don't need to classical signal because there's nothing left back in the originating nodes, right? I have this redundancy in the Bell measurements and I don't need classical signal. Should also say that we're making some assumptions about all the photons that are X measured making it. So in reality, this has to be redundantly encoded, but let's not worry about that for this talk. So my research is focused for this part of the talk. How can we generate such a multi-photon state, right? We kind of said, okay, if I had this multi-photon state, then I'm very happy because I don't need these long-lived memory qubits. But we haven't yet answered the questions of how to create these. So you can create them in two ways. One way is a probabilistic generation. And this is what most people have done up to now. For example, you can start with 6 qubits, pass them through beam splitters, make measurements, and then upon a particular outcome, you can end up with a 3-photon GHZ state, right? So here you have to be lucky because you only get the state you want 1 out of 32, with probability of 1 over 32, right? 1 out of 33 times. The rest, the vast majority of the time, this will fail, and you just have to start over. And there was an analysis of how well these protocol works that I just described. This is a little bit of a variant on the protocol I described. But anyway, it was a little bit of a pessimistic take that you need 1 million single photon sources per node to make this protocol work, right? However, you can hope to do much better. You can hope to use quantum emitters. So now we're bringing back matter qubits, but hopefully in a way that's not as stringent as requiring them to be super long coherent. And how do I create entangled photons out of emitters? The simplest thing you can think of is to create the state you're interested in the emitters, and then do some swap operation and emit a photonic state that mirrors the state you started off with, right? So this needs as many qubits as photons, but you can also do something else. You can have a smaller number of emitters and then use time as your additional axis, so to speak. So you can pump out entangled photons at a single step, 3 over here in this example, but then you can repeat this pumping process such that you end up with essentially the same thing, only that now you're trading off spatial with temporal resources. So this can be more practical because I don't have that many emitters that I can entangle very well with each other. And a lot of the work I'll tell you about was based on early proposals, both by this paper from 2005 and then later work of Terry Rudolph, where they looked at quantum dots and how you can pump them to create these kind of states. There's been several experiments now on this, both with quantum dots and with atomic qubits. And they all talk about how to, or they all demonstrate generation of either a single strand of graph state or GHZ state. What we want is those repeater states that are more complicated. And my group showed several years ago now how you can create this with 2 qubits. So this is going to be a cartoon where one qubit emits photons and the other qubit is auxiliary to help you grow the graph in the correct way. So we're pumping this emitter qubit, we're generating photons, which are the green, and then we're decoupling the emitter. And in the meantime, we're just hooking on through this procedure. The photons are hooked on to this longer lived qubits that did not emit the photons. Then I can repeat this process. I can re-entangle, pump, and create another arm. And then if I do this multiple times, I can Y measure. I didn't tell you what Y measurement does. What it does is it decouples this and unites all its neighbors. So I can actually get exactly what I want with 2 qubits. And we can also get error-corrected version of this. I'm not going to go into details, but you can add more qubits and get something that's redundantly encoded. Right, so then you can ask, okay, how did you know in this previous example that you needed 2 qubits? Right, well, I didn't know it up front. My student played around and came up with a protocol that uses 2 qubits, right? But if you really want to create error-corrected versions of this, then you should worry about what kind of resources do you need? So you know that you'll need more qubits, but how many more? And how do I need to pump these qubits? So that's the very last thing I'll show you before wrapping up, is a more recent work that we did, where we answered exactly this question. Given an arbitrary photonic graph state, how many emitters do we need to produce it? And how do we produce it? And I just want to mention that this problem is distinct from just circuit compilation because it's a very heavily constrained problem. All the photons don't exist up front. They're generated through this emission process. You can mathematically model this as a C0, but that's the only C0 you ever allow that photon to have in the circuit. And the photons are not assumed to interact with each other, right? We're imposing that constraint. So it's a very, very heavily constrained circuit compilation, so constrained that you should not view it as such. Instead, how you can view it is you can view it like a reverse engineering problem. And I'll just outline this work, which was done by Bikun Lee, a really very good student who's now postdoc in Chicago. So the idea is to start from the graph state you want to produce. And the red here is the photons, the green is the emitters. And then you can do a trick where you put these photons in a line, you draw their connection, and you can essentially use the entropy as your metric. And the entropy tells you, if you take cuts at every point, the maximum of this function, if I look at the entropy as a function of the cut, it tells me how many emitters I need. Moreover, I can generate these states with just Clifford gates, and Clifford gates are classically efficient to simulate. So I can work my way backwards in an efficient way and come up with, if I start with this, then what do I need to do to absorb the emitters, the photons with the emitters? And what kind of reverse measurements do I need on the emitters, which when I run the circuit the other way will be actual measurements. So it'll be a physical thing. So by using these ingredients, you can actually make a recipe of what you need to do. The one thing I want to point out is that you need to number your photons. That you can view as a bug or feature of this approach. Experimentally, you might want to actually impose some order they come out. And you can also vary a little bit these repeater states. So you see that for different numberings and different versions of these states, you have a different emitter count, and the circuits look are fixed, are generated through this procedure. All right, so this is my last, I think it's my last slide. How am I doing this time? 2 more minutes. Okay, great. Then it's not quite my last. So one thing I want to demonstrate here is that if I look as a function of the number of photons in the graph, how many C0 gates I need, which is essentially telling me something about how complicated the circuit is, they scale polynomially. And also to calculate what the circuit is, I also need classically polynomial resources. And this was done for just random graphs. So this is an efficient way to do it both classically to come up with a circuit, and the circuit itself is efficient. All right, so if I may, actually, if there's any questions, maybe I'll stop here to see if there are questions. Yeah. This one? Yeah, sure. This one. Yeah. I can repeat the question.
So then what is the advantage between this and this protocol? And my follow-up question is that you've drawn very specific graphs and sketches.
Yeah.
I realize it's on the direction. Decide what to do, direction and focus. What kind of limitations do you have on the actual graphs that you can generate?
Yeah. Yeah. So let me repeat. The first question was that this Bell state measurement is probabilistic here as well, right? And we talked about how Bell state measurements are probabilistic, and that can be an issue. Here you have a lot of redundancy. So you're okay if a bunch of them, even the majority, fails, because you can repeat. So at the limit where this graph is large enough, you can calculate the probability. You just need one to succeed. The ones that fail, you can just measure away their neighbors, and they don't impact the rest of the circuit. Yeah. And the other question was that you need some error correction, indeed. So these photons, the inner photons, these photons can even be lost, some of them, because a lost photon I can think of as a failed Bell measurement. But these inner photons, they better be there, because if, you know, this succeeds, then the neighboring photons should be there, because I want to measure them in the X basis. So those I want to encode in a redundant way such that I can tolerate loss. So there's some loss tolerant codes I can have for this inner thing, inner photon, and I can generate, that will take, of course, more temporal resources, and also presumably some more coherence resources, and more qubits. But using the protocol I showed you in the end, you can actually, you know, put in your favorite loss tolerant code and see, okay, which one compared to different codes, for example, because there is a way to generate both of them following the recipe I showed later. Yeah. Thank you.